All right, this is a continuation from the previous note. We're looking at electron configurations. In the previous note, we looked at how the electrons stack up in their energy levels. And to draw those energy levels is a little bit time-consuming and tedious. And so scientists are always looking to find easier ways of doing things. And so based on the Aufbau principle and the Pauli exclusion principle, we've made up these electron configurations to make them as simple as possible to understand. And so we have this line electron configuration which can be written out. So if we go back to our iron example from the previous note, it will look like this. So the 1s has 2 electrons in it. The 2s has 2 electrons in it. The 2p orbital has 6 electrons in it. We stack them up, 3s, 3p, 4s, and then we get to 3d, it happens to have just 6 electrons in it. Now the assumption is made that it follows the Pauli exclusion principle and the Aufbau principle. All right, so we have that assumption. But then if we get into the really big atoms, our electron configurations can be really long and tedious to write out. And so the shorthand has been used to make that a little bit easier. And so what we do is we go back to the nearest noble gas previous to the element that we're looking at, and we write that in brackets. So if we're going to do for iron, the previous noble gas is argon, so we use the argon configuration, we write that in square brackets, and then we go 4s2 3d6. One of the things that we will come across as we look at electron configurations is that if we follow the Aufbau principle and we follow the Pauli exclusion principle, and we find that there are some configurations which don't seem to make sense at first glance. And so because they actually violate those rules. And so we're kind of left wondering, okay, why is that? So I've got some examples here. So chromium, copper, molybdenum, silver, gold. The expected electron configurations are a little bit different than the actual electron configurations for these atoms. So let's take a look at chromium first of all. What we find is that chromium actually has an electron configuration that is, okay, based on argon. That's the lower part. But then instead of following the 4s2 3d4 pattern that we would expect, it actually goes 4s1 3d5. Leaves you scratching your head. Okay, so let's take a look at copper. Copper does something very similar. Instead of going argon 4s2 3d9, the actual configuration is argon 4s1 3d10. And if you look carefully here, there's something you should notice. The first thing is that instead of 2 electrons in the s, there's only 1. In the chromium, instead of 4 electrons, we've moved that up to 5. Okay, let's look at copper. Same sort of thing. Instead of having 2 electrons in the s, there's only 1. And instead of having 9 electrons in the d, we've actually moved it up to 10. So what seems to have happened here is that we've taken the s electron that should be there and promoted it to the d orbital. Well, what's happened in this case of chromium? In the case of chromium, we now have 5 electrons. We could have a maximum of 10, but there's only 5 there, so it's half full. In the case of the copper, we can have 10 electrons, and we've actually filled it right up. We filled up that d orbital. And so it turns out that there's something about this arrangement of the electrons which makes the atom, the electron arrangement around the atom, a little bit more stable. And so it's a preferred configuration over the expected pattern that we should have been following using the rules. All right. So what we see in most of these anomalies is there is actually a reason behind them. Okay, and practically speaking, these half-filled d orbitals or even s orbitals tend to give a little bit more stability to the atom overall, and so it's preferred over the other arrangement. All right, so what we see is that there are actually a number of anomalous configurations for the d block elements and for the f block elements. And some of them have obvious reasons for their anomalous configurations, like the half-filled orbitals or half-filled d orbitals, which tend to be more stable. Okay, there are some that have very odd electron configurations, and at this point the reasons for that aren't immediately obvious to us because we don't have a little bit more of the background that we need in order to be able to explain them properly. So we're going to leave those for upper university levels. Suffice it to say that the configurations result in the atom being slightly more stable than if we were to follow the rules. Okay, and so we go with those anomalous configurations and explain them thusly. All right. Now, we can also use electron configurations to predict what we call the ion charge. So, for example, magnesium forms a magnesium 2+ ion. So why is that? What's happening there? Well, the configuration for the normal magnesium is the 1s2, 2s2, 2p6, 3s2. For magnesium ion, well, it's these two 3s electrons that are given away to leave us with the 1s2, 2s2, 2p6 configuration, right? So again, this is a filled orbital, and so that's stable, and that's why that configuration shows up. We can also use that for explaining the negative ion configurations. So let's say for nitrogen. What happens in nitrogen? Well, nitrogen normally forms a 3- ion. Well, why is that? Well, it normally has, the nitrogen has a 1s2, 2s2, 2p3 configuration. Well, this p can hold a maximum of 6. So if we put 3 more in there to fill it, now we have our full 2s, 2p orbital, and so that means that we have the N3- ion. And again, that gives us a stable configuration for that. All right, so that's where that 3- charge comes from, because we've dropped in 3 extra electrons to fill up that p orbital. All right, copper, same sort of thing. If we look at the actual configuration, it is anomalous, but if we look at that actual configuration, the charges for copper, well, we would expect that if we leave this full and we have a 4s, one electron in here, if we remove that electron, then we get an argon 3d10, and that would give us a 1+ charge, right, for the copper. At the same time, if we kind of go back to the following the rules, and we remove this one plus one of the d electrons, then we end up with this argon 3d9 configuration. We get a 2+ charge on the copper. Okay, so these are the configurations here for how copper loses electrons to form the 2 ions that we see as the primary ions for it. Okay, tin. Tin makes tin 2+ and tin 4+. So let's take a look at how that works. So tin has the krypton root and then 5s2, 4d10, and 5p2. So if these 2p electrons, or 5p electrons, are removed, then we get tin 2 plus, right? So we get 5s2 4d10. The other one is the tin 4 plus, and so with that one, if we remove, because now remember when we're way out there at the 5 and 4d 5p, those orbitals are very, very close to each other, and so in this case, leaving that 4d full is more of a stable configuration, and it's easier to pull out the two 5s electrons along with the 2p electrons, and then we get our krypton 4d10 configuration for the tin 4 plus. All right, so that's kind of how we explain those configurations. And again, this configuration with the 4d10 leaves it very stable. Okay. There are other properties that we want to be able to explain. We can use our electron configurations to help us with that. The first one is what we call the magnetic properties of the transition metals. You'll notice that iron is a magnetic compound. It can have, it can behave like a magnet, and we call that ferromagnetism. Ferromagnetism it results in the fact that the 4s2 3d6 configuration has a very interesting look to it. 4s has 2 electrons, and then 3d has 3 unpaired electrons. Actually 4 unpaired electrons, because the configuration looks where the first suborbital of the 3d is filled with 1 electron spin up, spin down, and then 4 unpaired electrons. All right, so it seems that having the pair of electrons in the first d or a suborbital and unpaired electrons in the others gives iron the ability to be magnetized. So when the spins, the way it's explained is that when the spins of the d or electrons align, their magnetic fields apparently add together to enhance the magnetic effect. All right. So what we end up then is in normal iron, we get these domains where electrons line up, okay, and you get a whole bunch of iron atoms that in a little bit of a section in there where the magnetic fields then also line up. In normal iron, there are different domains, we call them. So groups of iron atoms where the electrons spin together, and so the magnetic fields line up. But these groups are not aligned with each other, and so the magnetism is a little bit more haphazardous, and the magnetic fields kind of cancel each other out over the entire lump of the metal. When you align those domains with an external magnetic field, then you get the magnetic fields of each of those domains adding together, and you create what's called a ferromagnet, or an iron magnet. Okay. Elements like cobalt and nickel, they also have some unpaired electrons in that d orbital, but because they don't have as many electrons, their magnetic fields are much weaker, and so their domains are forced to align by only by an external magnetic field, and this is what we call paramagnetism. So nickel, for example, 4s2 3d8 looks like this, and then the first suborbital is filled with 2 electrons, the second one as well, and it leaves 3 electrons, and the third one as well, and then it leaves 2 electrons that are unpaired. Okay, so on page 199 and 204 in your textbook, have a look at those questions that talks a little bit about paramagnetism and ferromagnetism. And we'll leave you to ask questions as you come across difficulties with that.